The next piece when looking at stoichiometry is to look at limiting reactants. Limiting reactants are the case where we have set amounts of each of the reactants and we need to figure out which one is going to determine the amount of product that can be produced. When we have reactants that are not present in the exact mole ratio, so if it's a 1-to-1 ratio, if you don't have equal number of moles of each reactant, one of the reactants is going to be used up before the other reactant. The one that is used up is known as the limiting reactant. We can calculate which one is the limiting reactant, how much of the extra reactant is left after the reaction is taking place. We know this is the excess reactant, and the amount of product that is produced in the reaction. I think it's easiest to talk about this by looking at an example. So let's look at this example here. You've been hired to be the manager of the Woodward Academy Deli. We're going to put a deli into the student center, and you're going to be the manager, and you need to do some basic calculations. You're going to make a sandwich for your deli. The deli is quite simple ratio. You're going to have 2 slices of bread, 3 slices of meat, 1 slice of cheese to make a sandwich. We're not going to worry about all the condiments here. So now suppose you go into work and you have the following thing. You have 200 slices of bread, 240 slices of meat, and 120 slices of cheese. How many sandwiches can you make, and what will be left over, and how much will be left over? So this is a typical limiting reactant problem. You have a reaction, in this case are 2 slices of bread, 3 slices of meat, 1 slice of cheese, forming 1 sandwich reaction. We'll do it with chemical reactions in a minute. And we want to figure out what we're going to run out of, because the thing we're going to run out of, once we're out of it, we can't keep making any more sandwiches. So it's going to be determining how much of the products can be produced. It will be known as our limiting reactant. So we can start with the bread. You have 200 slices of bread. We require 2 slices for every 1 sandwich. So from the bread, we can make 100 sandwiches. And this is the method we want to use for limiting reactant problems. Start with each of the reactants and determine one of the products. In this case, there is only 1 product, sandwiches. But if you have more than 1 product, convert them all to the same product. Now, with the meat, you have 240 slices of meat. Each sandwich requires 3 slices. So when you do that conversion, you could make 80 sandwiches from the meat. And finally, from the cheese, we have 120 slices of cheese, and each sandwich requires 1 slice. So you can make 120 sandwiches. So we could make 100 sandwiches from the bread, 80 sandwiches from the meat, and 120 sandwiches from the cheese. So since we can only make a total of 80 sandwiches, because after we make 80 sandwiches, we are going to be out of meat. Meat is our limiting reactant. It's the one that's going to be used up first. We're going to have extra bread and cheese. Since you can only make 80 sandwiches, you'll use 80 times 2, 160 slices of bread, and 80 slices of cheese, since there's 1 slice per sandwich. If you started with 200 slices of bread, that means you're going to end up with 40 extra slices of bread. If you started with 120 slices of cheese, you're also going to end up with 40 slices of cheese. We can do the same thing with any reaction. So here we have zinc being added to hydrochloric acid to form zinc chloride and hydrogen gas. So, first thing to do always, just as we've been doing with any stoichiometry, is write the balanced equation. So zinc plus HCl forms ZnCl2 plus H2, and the balanced equation is 1 to 2. Start with each of the given pieces of data. So 1.21 moles of zinc, 2.65 moles of HCl. Convert them to one of the products. In this case, we want moles of the products, so I'm going to convert to moles of one of the products. So in this case, I'm going to choose ZnCl2. It doesn't matter which one you choose for this step, as long as you are consistent. So this is a 2 to 1 ratio. Remember, the ratio comes from the balanced equation. So 2.65 divided by 2 gives us 1.33 moles of zinc chloride. For zinc, we're going to go to the same thing, to zinc chloride. We get 1.21 moles of zinc chloride. So what this tells us is if all the zinc reacts, we'd make 1.21 moles of zinc chloride. If all the HCl reacts, we'd make 1.33 moles of zinc chloride. That means we can only make 1.21 moles of zinc chloride, because once we've made that, we ran out of all the zinc. There will be extra HCl left over. So zinc is our limiting reactant. Now it asks us a couple other questions here. We want to know how much extra HCl we have and how much of each product. So once you've figured out the limiting reactant, it just becomes stoichiometry with all of your conversions, and you have to do them starting with the limiting reactant. So let's convert to HCl. So if all the zinc reacts, we would need 2.42 moles of HCl. Since we started with 2.65, we used 2.42, we'll have 0.23 moles HCl as our excess. And finally, 1.21 moles of zinc, 1 mole H2 for every 1 mole HCl, so we would produce 1.21 moles of hydrogen. So when this reaction takes place, all the zinc will be used. We'll produce 1.21 moles of zinc chloride and 1.21 moles of hydrogen, and we'd have 0.23 moles of HCl remaining. Okay, here's another example. Steel wool is heated until it glows. It's placed in a bottle containing pure oxygen. The iron reacts spectacularly and produces iron 3 oxide. If 1.25 grams of iron is heated and placed in the bottle, what mass of iron 3 oxide is produced? So first we start with our balanced equation. Fe plus O2 forms Fe2O3. So our balanced equation, 4Fe plus 3O2 forms 2 Fe2O3. Take each given piece of information. And we need to convert it to the product. So in this case, our first step is to convert to moles. Iron has a molar mass of 55.85 grams per mole. There are 2 moles of Fe2O3 for every 4 moles of Fe. And we're looking for mass, so for every 1 mole Fe2O3, we get 159.70 is the molar mass. Okay, we multiply out 1.25 grams divided by 55.85 grams of Fe times 2 divided by 4 times 159.70, and we get 1.79 grams of Fe2O3. Now we need to do the same thing with oxygen. We need to convert it to grams of Fe2O3. In this case, we're starting with moles, so we're going to do 2 moles Fe2O3 for every 3 moles O2 from the balanced equation, and then 159.70 grams Fe2O3 for every 1 mole Fe2O3. So 0.0204 times 2 divided by 3 times 159.70. We get 2.17 grams Fe2O3. So if all of the iron reacts, we produce 1.79 grams of iron 3 oxide. If all of the oxygen reacts, we produce 2.17 grams of iron 3 oxide. So that means in this case that iron is our limiting reactant, and we would produce 1.79 grams of Fe2O3. Okay, this next problem, I'd like you to try it on your own, and then, so press pause on the video, try this on your own piece of paper, and then come back and see the way that I solve it. So the problem, how much of the solid product is formed in each of the following reactions? So in this reaction, we have 50 grams of each reactant. We have NH3 plus Na forms NaNH2 plus H2. We do need to balance this reaction. So we have one Na, one Na, one N, one N. We're not balanced on the... So we're going to put a 2 for Na, 2 for Na2, NH, and a 2 here. That gets us to 6. 2 nitrogens, 2 nitrogens, 2 sodiums, 2 sodiums, 6 hydrogens. We have 4 plus 2, 6 hydrogens. So we have 50 grams NH3 and 50 grams Na. First step, convert each of these to the solid product. So we're going to first need to go to moles. 1 mole NH3 over 17.04 grams. Then the mole-to-mole ratio, so 2 moles NaNH2 for every 2 moles NH3. And then 1 mole NaNH2 and 39.02 grams. For this one, 1 mole Na, 22.99 grams. Another 2-to-2 ratio. And then 39.02 grams for 1 mole NaNH2. So this top one will give us a mass 50 divided by 17.04 times 2 divided by 2, so it's just like multiplying by 1, and then times 39.02 to 3 significant figures of 114. And the second one, 50 divided by 22.99 times 2 divided by 2 times 39.02, and we get 84.9. So 84.9 grams is our answer. So with each of these limiting reactant problems, we need to start with whatever we're given for each reactant, convert it to grams of one of the products. Whichever one produces the least amount of product, that answer will be the amount of product that's produced, and that original reactant will be our limiting reactant.